May I now request all the panelists to come to the... Yes, please go ahead with your question. Yeah, Satya and
okay.
Could you please come up?
I don't know if Satya or for Souradeep, you decide who answers. So at the moment, LIGO has bounded the number of intermediate mass, black holes of 100-ish, below 1 gigaparsec cube per year. So if this bound keeps going down, when will come a tension with the formation of second-generation black holes?
I have. Actually, can you
sure.
ask me?
I mean, we know now that we don't see intermediate mass black holes, right? A few hundred solar mass black holes, we don't see them with LIGO. So we have upper bound. This upper bound is, I mean, either we have a detection or this upper bound will keep going down. So how down should it be to create a tension with your picture?
I think you're talking about the second generation mergers.
Yeah, second generation.
So the conventional wisdom is that there is nothing produced in the mass gap and it's only coming from this. And as I see in this case, so there are two mass gaps. In the heavier mass gap case, it looks like they must be observing these heavier black holes soon, because maybe every 1 in 20 should be of that kind. So the prediction might be that if you don't observe 1 in 100, that's severely constraining, but they expect to observe something like 1 in 20.
Basically, the actual lower bound can go down, say, by a factor of 10-ish, not more.
Yeah, exactly.
I think that the way you asked the question can be a little confusing in the following way. So IMBHs can be much larger black holes, and that's a completely different issue. So if you are asking about second generation mergers, so anything above, say, 100 or 120-ish solar mass, pre-merger, or total mass after, if you don't see any after 100 detections, then yes, we'll start worrying. But we will not really worry, because that will probably say something about the birth spins. Because remember, the retention fraction of merged products depend on the birth spin distribution.
I suspect that the second generation, the first generation are mostly roughly comparable masses, so the kick should always be small.
So we have small spins and comparable mass. Therefore, the kicks are small, and therefore you should expect the greatest number of second G mergers is what Ricardo is arguing.
If you after the detection filter, I think it's few to 10% should be 1G, 2G.
So, okay, a couple of questions. First, for Saurav, but channeling something that Satya passingly mentioned, if we observe more binary neutron stars, that has implications on binary black hole merger rates, right? How tightly are these two formation rates coupled? Can you say something about that?
In fact, the related question is, do we expect binary neutron stars and neutron star black holes form in the same environment as binary black holes? I don't think we know the answer to this.
Okay, so let me give a multi-stage answer to the question. Okay? So we are actually writing a paper now about binary neutron stars coming from star clusters. And the title is, are clusters efficient in creating merging binary neutron stars? And in the current version, the abstract is a single word abstract. It says no. And the reason is mass segregation again. So until you eject most of the black holes, the neutron stars don't get to enter the high density region, and they don't take part in dynamics. Now, the second stage of the answer is, the binary neutron star merger rate is so high that no one knows how to make this without significantly increasing the binary black hole merger rate, which to a level where it becomes inconsistent with the merger rates predicted by LIGO. You can play with the initial stellar mass function. So by playing with that slope, you can always change the relative number of black holes to neutron stars. But from observation, at least in the local universe, we don't have a lot of flexibility. So for example, if you take a Krupa type IMF, the error bars will not be sufficient to create or increase binary neutron star production significantly without increasing binary black hole significantly. It's a problem.
Thanks.
The very model that tries to explain binary black hole ray has killed the binary neutron star.
Yes.
So I have a small clarification from question, something I have not understood in your talk. So apparently the effective spin becomes, can be zero at the end. We can explain why it is close to zero in the dense cluster scenario. So why is it so? Why can we understand this? Because it's not in average, it's for each event.
I think it's again not well understood.
Right.
We should expect, one has to have a distribution for spins. If they were aligned, we would have been more sensitive to it. We would have seen 10 times more of those events. We don't. So it is a mystery as to why. I don't think he's saying, he is assuming different cases.
Okay, I see. Thank you.
Not saying that.
So those are just assumptions. Since we don't know, we take zero.
Okay, sorry, I misunderstood.
Okay, so this is again a question. I mean, I was quite taken aback by the statement that that this encounters of black holes, right? And before they, not the ones who actually form binaries, but which, prior to formation of binaries, would give rise to bursts. And furthermore, these are going to be much more common than something like mergers. So I mean, so there must be lots of burst signals then these people should be seeing. And my sort of puzzling question is two really. One is an observational thing, I mean, why one doesn't see that. But secondly, also theoretical thing, namely that why have a numerical relativity or analytical people or something not focused on this and work this out? I mean, you said you are about to work it out, but it seems to me that, you know, it's a...
I think I can...
No, but
yeah.
much more than...
Korea, they have modeled these encounters, one-off encounters in numerical relativity wise.
So I think the qualitative answer is this. If the bursts are strong enough that they get very close, then they will be captured. If the scattering is from a large impact parameter, then the gravitational waves will be weak and we won't observe them. So there's only a critical distance in the impact parameter where it will be observable, but that number may not be large enough.
But there must be lots of them nearby as well, right?
So actually,
Close by.
Yeah, there must be lots of them nearby also, so one should have been seeing them. I mean,
They could be in band. If they are close enough, that's why
I think most of the encounters will be slightly
larger impact
larger
means they will be out
pericentric,
of
so they
band.
will be in LISA band or something.
there are two issues. One is the distance between them, and the second is the whole binary distance to us. So they could have been, I mean, in the nearby globular clusters, there could be such things, right? And then even if the impact parameter is not so small, just because they are so nearby, we should be able to see them. So I think one should be able to estimate.
That would be in the LISA band is what Teja is pointing out.
It's going to be LISA. Why is
Could
that?
be. Oh, because
it will be
larger impact.
larger impact parameters, so it will not be in the 10 hard. But what you can argue is these will probably be very high eccentric. So there is no orbit, right? So it's during a strong encounter. So it's probably in the parabolic limit with very low or low enough impact parameter. So an interesting question that we haven't worked it out so far would be, can there be enough harmonics, and will that be strong enough to be pushed to, I doubt it will be pushed to LIGO, but it may be something in the middle, like 0.1 type detectors. It can be very interesting there. So just to so related to your question, so this is I'm showing the peak peak strength and the frequency, and this is the strain. Okay, so these are all the binary black holes that are created, and we assume that everything is created at 500 megaparsec away. Okay, so the blue are after ejection, the red are in cluster, and these are the gravitational wave capture. So the captures are happening somewhere around here. So these dots are where they're forming. Okay? So already at few times 10 to the minus 2 frequency, you can see that it has been captured, and it will then become a binary and merge very soon. And the time scales for mergers are tiny. So if you want something that will not be captured, but only create a burst and then go away, unbound, that will be even lower frequencies. So that's where the problem is.
But of course, it's 500 megaparsecs, you said, right?
Yes.
So,
yes.
I mean,
so close
I was talking about nearby, yeah.
Right.
Go ahead.
So I had a question for about one of your slides where you mentioned that a fraction of the events, BBH mergers, that should be detectable by LIGO are actually eccentric. I'm just wondering if there's any estimate. Maybe there was a talk earlier that made an estimate, but I don't remember. Is there an estimate of how many of these we would miss, or we have missed in O1 and O2, given the sensitivity and the rate that you mentioned?
I don't remember exactly. This was written about a year ago. So I think this is what we asked our LIGO experts, and that's where the limit is. So with the template matching search, I think there is a very good chance that these will be missed.
I see. And this n is, so this is not a rate, is it n divided by, yeah.
This is n over n total.
Okay.
So since you asked the rate, and I forgot to mention this point, rates are uncertain. So we understand the dynamics very well. We don't quite understand the supernova physics, but we at least have some prescription. But to fold that into a rate number, you need globular cluster formation histories, globular cluster number density as a function of redshift. Both of these numbers are severely incomplete and has uncertainties. So that actually creates most of the uncertainties in the predicted rates.
Rashmi?
Yeah, there are some results which say that with the future sensitivity, there may be a tail of BBH events which could have so small a localization to get the host galaxy at least probabilistically identified to some extent. If that happens, will that anyway give any kind of inputs or constraint to the formation scenario?
I couldn't really hear.
So can we place any constraints on just the rates?
Can we place any constraints on the formation scenario if we know the host galaxy identified for a BBH with that kind of localization?
So can I?
No, you go ahead.
So there are two ways that you can go about solving this problem. One is at a population level. So you have large numbers of detections, you look at the property distributions, and you do an apples to apples comparison. So all stellar evolution physics you keep fixed on both sides. In one case you have dynamics, in another case you do not have dynamics, and you compare the two distributions. A completely different type of test would be you see one so-called flag bearer event. For example, it has a pre-merger mass that's above what you expect black hole masses to be, or it has very high eccentricity, if it has very high negative chi-effective. So these would be flag bearer events. And if you get one such event, then you can clearly say that this cannot be created in isolation. So there are these two different ways you can go.
Yeah, but the primary thing is we won't be able to identify for binary black holes by no means what the host galaxy is, unless they emit electromagnetic radiation, which has
Localization also. Yeah.
So localizing if you can localize the galaxy, what will be really nice is then you probably can, if it's an elliptical galaxy, you can probably put better constraints on the metallicity and redshift. So if you know redshift and metallicity, then you are reducing the parameter space by a lot, and then you only have a lower range in black hole masses to play with. So I think it will be helpful if you can do it.
Chris and then Patrick.
So I can just quickly comment on that last point, because that's some information that we currently input into the Hubble constant analysis very, very weakly based on properties of galaxies that we weight, but that could be extended and flipped round to infer those things. But it's going to be statistically averaged over lots of galaxies within the error regions. But my actual question was to Jasvi. I can understand how you can get a different set of binary detections. You've got a different background analysis and things like that. Can you comment on how similar the posterior parameter estimates are for the common detections? Do you agree?
We detect all the LVC events.
No, but the parameter estimations, do the masses match up? Do the sky locations match? Do spins match? Because it...
Yeah.
Okay.
Yeah.
I don't think they have found any controversial thing with what LVC have found. It's just that they have found more events.
I just couldn't quite tell. There was lots of contour plots and it didn't look like contours were overlapping exactly, but maybe I was misunderstanding.
Because I think for the contour plots of the posteriors I made, I used this uniform chi-effective prior. So it's not the same prior that the LVC uses, so they will not be literally the same posteriors. But yes, we did the test where we did it with the LVC prior and got the same posteriors.
Okay.
Yeah, my question is to Saurabh. When you were calculating the rates of two black hole encounters and the burst of gravitational waves, one would expect that the dynamical friction would play a very big role in the globular cluster environment, and the two black holes would actually get slowed down. So probably the capture rate, if one includes the dynamical friction, should be higher. So in your analysis, did you take into account the dynamical friction apart from the gravity between the two black holes?
So actually the dynamical friction is, so the kinds of encounters I'm talking about, dynamical friction is not that important because the length scales for these, so these are not supermassive black holes merging, right?
Yeah.
So these are tiny black holes compared to supermassive black holes, and the length scales for these orbits are a few AU. That's really a point compared to the whole cluster. And the time scale for these encounters is a few years. So that's an instant. So nothing really happens. You can totally disassociate the strong encounters from the two-body relaxation process. And because these are resonant type interactions where things just keep dancing around for a long time, you can order of magnitude estimate what fraction of these encounters will end up having enough gravitational wave radiation to make something bound just by looking at the phase space. So you look at the phase space for how much V over C you need, and you start with some V over C, and the volume ratio of the two phase space will give you exactly the ratio between the two histograms I was showing.
If you're looking at these two black hole encounters near the core of the globular cluster, where the density of the stars or other heavy objects are larger, one would expect that the dynamical friction would play a role near the core, even if you have 1 AU separation. It depends upon how close are you to the core of the globular cluster, right?
So most of the interactions are happening deep inside the core.
Right.
The typical the typical densities are about 10 to the 5 solar mass per parsec cubed. Okay. So dynamical friction takes a long time to affect things.
Sure.
So these are so quick and happening in such a small volume that I don't think during the interaction, dynamical friction will play a significant role.
In view of the time, last question.
Just last. So, very quick question. So, what is the number density in the after mass segregation in the core, and what are the maximum mass that you expect in the core? Like just a typical range over different globular cluster scenarios.
So the typical densities go from about 1,000 solar mass per parsec cubed.
But the number density, am I saying number density?
Number density.
Number density.
Allow me to change the question because because the question does not take into account some of the details. Okay. So what you are not interested in is an average core density. What you are really interested in is what is the density of, say, the innermost 10 black holes. Okay? So the innermost 10 black holes, that density, I think I have a figure somewhere. It can be 1 million solar mass per parsec cubed. So divided by roughly 10, so 10 to the 5 number per parsec cubed. Let me see.
So the typical masses will be 10 solar masses, maximum of 200, you mean, something like that? No, per black hole.
Let's take a look here. So this is, say, 10 to the minus 3 per sec. And at the deepest collapse stage, that's the most dense stage, it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 black holes.
10 black holes. And each black hole will be something like 10 solar mass, not more than 100, something like that?
That depends on when. Because due to mass segregation, you start from the highest mass black hole and then keep ejecting them and then the lower mass.
Okay.
On an average, if I want to say give you one number for an average mass of a black hole, it will be between 10 and 14.
Okay, thanks.
All good things must come to a stop. Despite the fascinating nature of this discussion, we will conclude the session now. Let's thank all the panelists.